Hello everyone and welcome to another one of Mr. Martin's videos. This video is for Physics 12 students in British Columbia using the BC Science Physics 12 textbook from Advantage. We're going to be looking at Chapter 5, Section 2, looking at gravity and Kepler's solar system. BC doesn't want to hear anything about Kepler. So Kepler's solar system, much more popular here in BC. So first let's look at falling objects. So here, if you have these three objects in this slide, okay, we can see based on what we know about an object in free fall, which is an object that only the force of gravity is acting on, all three of these objects are in free fall. The first object is just being dropped and dropping straight downward. The second object, we can imagine that it's a ball being thrown horizontally to the right. So it's got a horizontal component, but the vertical component doesn't change. It falls just like the first object and would hit the ground at the same time, barring all other variables, if all other variables remain constant. And then the third ball is a ball that was thrown upwards, but the moment it leaves the hand, the only force, even though it's traveling upwards, it's being slowed down by gravity and then accelerated by gravity, and only gravity is working on it, accelerating all three of these objects at a rate of g. Okay? These are all free-falling objects. So Newton took this idea and he understood that the moon, looking up at the moon, he understood that the moon was also a free-falling object falling around the Earth. And this is how he conceptualized it, and it's really a helpful diagram for us to conceptualize gravity and orbiting objects around the Earth. So if you have this cannon, and this cannon is, above the surface of the Earth, and it shoots a cannonball with a certain horizontal velocity, that ball is going to travel and then, because of gravity, eventually hit the ground. Okay? But now you add more gunpowder into your cannon, because we got an old school cannon, and because it has an increased horizontal velocity, it's going to make it further than the first cannonball, but eventually hit the ground as well. Okay? And let's say we can increase the power or the force of this cannon, and so we get a greater and greater horizontal velocity. And eventually what we would end up with is a cannonball that is traveling so fast that as it's falling towards the Earth's curvature is kind of moving away from it. And so you have this cannonball that's falling towards the Earth constantly, but because of the Earth is curved, it keeps missing the Earth as it's traveling down towards the Earth. Okay? And so that's how a good way to kind of understand gravity or an object in orbit is an object that's being pulled down at every stage, at every point along its path towards the Earth, but because of its horizontal velocity being so large, and the curvature of the Earth being round, that the cannonball continues to fall towards the Earth but never hit it, because the Earth kind of dodges it by curving. So that's one way you can think about objects in orbit being in free fall. They are actually falling towards the Earth, but they keep missing the Earth because the Earth is round and not flat. Okay? Take off your aluminum foil hats, please. All right. So yeah, he created this diagram. Hopefully that's been helpful. We'll keep talking about this a little bit as well, and I'll try to demonstrate this in class together, our next class time together. But in the wording here of the book, he described the firing of a cannonball horizontally off the top of a mountain at ever-increasing speeds. Eventually, the cannonball is traveling so fast that it travels horizontally as much as the Earth's surface, I guess is the missing word there, is curving away. So the Earth is curving away from it, causing the cannonball to continually miss the Earth as it's falling towards the Earth. So hopefully you're able to follow that. If not, rewind the video, listen to that again, and see if you can make sense of that. So now the cannonball, if it's that fast, this last cannonball here, is now a satellite around the Earth. Okay, that's what we call a satellite. It's just something that's orbiting around our Earth. And the moon as well is a satellite because it's orbiting around the Earth. Okay, so that's just to help us conceptualize what it means when an object is orbiting around the Earth, and what does that mean for gravity, and what does that mean for, free fall and all these things. That's what's going on here. Okay. Now, Newton postulated that there was a centripetal force that must be keeping the moon in orbit, right? If there was no force between the Earth and the moon would not be turning around the Earth. Because of Newton's first law of inertia, the moon would just be moving in a straight direction away from the Earth. Okay, but it keeps curving towards the Earth. Something is pulling it towards the Earth, and that force we know, of course, is the force of gravity. That's the only force between Earth and the moon, at least the most significant one. Using known values for the period of the moon and its distance from the Earth, Newton was able to determine the centripetal acceleration of the moon as it orbits around the Earth. So, using this formula, which should be familiar to you guys by now, and knowing the distance that the moon is from the Earth, and then the period of the moon around the Earth. And so here, for some reason, they have a 25-hour day instead of a 24-hour day. But otherwise, that's the numbers they use. You're able to solve for the acceleration due to gravity, which is the centripetal force and a centripetal acceleration of the moon towards the Earth of this value here. Now, you say to yourself, well, that's not g. The Earth pulls things with an acceleration of g. Well, that's only at the Earth's surface, okay? We also know that the gravitational pull of an object that is two objects that are further away is less than two objects that are close together. So g is actually calculated based on the radius of the surface of the Earth, and assuming that the object is being measured on the surface of the Earth, which is the majority of objects when we're dealing with physics. However, now we're going interstellar here into space, so that g is no longer the assumption anymore of 9.81. G is going to change based on the distance between these large objects in the vast universe. And so, and this also helped him, kind of realize that, Earth and that of the gravitational force must rapidly decrease as the distances from the Earth increases. Okay? And we know that's true based on Newton's formula for gravity that we talked about in Physics 11. Now, I want to talk about a couple astronomers here that made some important observations and measurements in the study of kind of orbiting objects. The first one is actually this Tycho Brahe. I don't know if I'm saying that name right. He was a astronomer that was able to make precise observations of over 800 stars and accurately record the planets over a period of 2 decades, so 20 years. And the amazing thing about this guy is that he didn't have a telescope to do it. Telescopes were not invented until years later. And so this guy did this without any of the tools that we have available to us today. And not just available to scientists today, like available to like kids that have a telescope in their bedrooms today. He didn't have that. He was just looking at things with the naked eye and being able to make those his accurate measurements that have been shown to be actually quite precise of 800 stars over 20 years, which is really incredible. And the next, person that we're going to talk about, Kepler, the person we mentioned at the beginning, Johannes Kepler. He had the opportunity to work with this meticulous astronomer, and he used his teacher, his mentor's notes, precise observations, to search for mathematical patterns in the motion of planets. So he took the data that Tycho Brahe collected and tried to find mathematical patterns in the motions of the planets that this guy had measured. And based on that data, he was able to formulate 3 laws that describe orbits of planets around the sun. So here are the 3 laws. Makes an excellent multiple choice, short answer question, these 3 laws, by the way. So just be mindful of that. Number 1, each planet orbits the sun in an elliptical path, with the sun at one of the 2 foci of the ellipses. And so here, when we think about an orbiting object, we always, or typically, think of an object in a circular shape, okay? Even though my circle is not perfect, we think of a circular object. But the path of satellites or orbiting objects is never really truly a perfect circle, okay? They're more of this ellipses shape, okay? With the kind of the source of the gravitational pull that's keeping the object in orbit at either one side or the other side of this oval shape, okay? At one of the narrow ends or the other narrow end of the oval shape. Okay, so that's important. It's not this perfect circle orbiting, just like Earth does not travel in a perfect circle around the sun. There's actually portions of the year where the Earth is closer to the sun than other portions of the year, and that is just represented in due to our elliptical path around the sun. Okay, now it can be pretty close to a circle, right? Like you can get pretty close to a circle without it being a perfect circle, but just to say that it's not a perfect circle. All right. The second of the 3 laws is, so this is kind of Kepler's diagram of this ellipses shape with the sun either being in one of those 2 kind of loci of this oval or ellipses shape. Now Kepler realizes well that a line joining the center of the sun and the center of any planet will trace out an equal area in equal interval of time if time intervals t2 minus t1 and t4 minus t3 are equal. The areas traced out by the orbital radius of the planet during the interval will be equal. Okay, so that's quite nice long description here. So what does that mean? Okay, so let's say between time 1 and time 2 was 30 days. Okay, so if I took the planet here and the planet here, and I knew that the time it took to get from position 1 and position 2 in the orbit around the sun was 30 days. Okay? If the amount of time from T1 to T2 is the same as T3 and T4, okay? So here he's saying that amount of time is equal to the amount of time it takes to get from T3 to T4. This is also 30 days, okay? And so if the amount of times, measured out is the same, 30 days, but at different locations in the orbital path. The area, that's shaded here in orange is going to be the same as, so the two spots are the same. So the area here is equal to the area here. All right. So let's choose another maybe 30-day spot. So let's do T, 2, 3, 4. Let's do T5 here, and maybe T6 here. Maybe T6 somewhere here. Okay. So you have a not so straight line there, and a little bit better line there. Okay. Let's say this is T5. And this is T6, and again, we're saying that the time it takes to get from T5 to T6 is 30 days. That's our kind of set time. The area now that I can shade in between the two lines that I've drawn will be equal to, wow, this orange almost perfectly matches the orange that the slide uses. Huh? Just a little bit darker. So this area now will also be equal to the area of the first two shaded regions. And that's true for anywhere in the elliptical. The shape of the area changes because the planets actually travel at different speeds at different points around the ellipses. But even though the shape of the shaded region changes, the total area of each shaded region does not change. Okay? Now, based on this diagram, where do you think the object orbiting around the sun here travels the fastest? Hopefully your answer was between T3 and T4, right? This is the fastest. Okay? And what's happening here is essentially it's getting a little bit like slingshot around the sun, and then traveling out here, and it's traveling then slowest out here, and then accelerating kind of back towards the sun and being slung out again. Okay? Now again, this is an exaggerated ellipses compared to the orbital path of the Earth around the sun, but this is still true for the path of all objects around the sun and all objects around the Earth that are orbiting the Earth as well. That is also true. Okay? So in order for this to be true, a planet during T4 minus T3 has to have traveled faster than during interval T2 and T1. And that's what we just talked about there. Okay? Now the third law is the mathematical law. All right? Kepler's third law of planetary motion states that for any planet in a solar system, the cube of its mean orbital radius, so that's average orbital radius, and so here the reason why we use mean or average orbital radius is because if we acknowledge now that an orbiting object it has an ellipses shape, you can see that the radius between, or the distance between the sun and any planet is not going to be the same the whole time, right? When the planet is over here, for example, it has a smaller radius than when the planet is over here. Okay, these are not equal to each other. This one and this one are not equal to each other. Okay, so that's why we use, for this calculation, we use the mean orbital radius, which is the average of all the radiuses or radii as the object orbits around its central kind of mass that's causing it to orbit, whether it be the sun to the Earth or the Earth to the moon or other planets to other planets. And if you divide, going back to this, if you divide the cube of this average orbital radius by the square of its period of revolution, you'll get a constant. Okay? For that planet. Okay? And you'll also get a constant that's true for any other planet for that same you know, source of gravity. Okay, and any other planets orbiting that same, you know, or any other planets orbiting the sun, all planets orbiting the sun will have the same k value. If you take their mean orbital cube of their mean orbital radius divided by the square of their period of revolution, all planets orbiting around the sun will have the same k value. Okay, that k value is defined for the source of the orbiting motion of the satellites around. Okay. So change in the solar system or orbiting system in the question, and you may have to have a new value of Kepler's constant. Okay, so you're going to get a k constant for the solar system and all the planets around the sun. You can get a different k constant for all the objects orbiting around the Earth, right? Because that's a different system. They'll have a different k constant. So the moon, the k constant of the moon around the Earth will be different than the k constant of the Earth going around the sun. But the k constant of the Earth going around the sun and Mercury going around the sun will be the same, and the k constant for the moon going around the Earth and some other satellite or the International Space Station orbiting around the Earth will be the same. Okay, so it's true for based on the originating mass of the orbiting motion. Okay, so let's actually do some math here with what we know about this. So we have a certain asteroid has a mean orbital radius. All right, this just means average. Okay, it's not talking about its character or how nice he is to people. So we have this R value of 5.0 times 10 to the 11 meters. What is the period of revolution around the sun? So here, I think in the textbook they had that constant already determined. So I'm going to go just check that out real quick, get that constant for us, and then we'll be back here in a second. So they had this example question, planet Xerox, just discovered by Superman on one of his excursions to the far extreme of our solar system. Its distance was this far away. How long will the planet take to orbit around the sun? And so here you have you use the values of the Earth, and so you need these values here to answer the question, because then if they're both equal to k, so if the r cubed, so this is my question here, so I'll just use this same as the slide here. If the r cubed for the asteroid over the t squared of the asteroid is equal to k, and that's equal to the r cubed of Earth over the period squared of Earth. If they're both equal to k, then we can get rid of the middleman, right? If they're both equal to k, then they're both equal to each other. So we can plug these values in for Earth, but we need the values for Earth. These are on your formula sheet, and they're also in our textbooks here. So I have an R value of 1.5 times 10 to the 11 for Earth cubed, divided by the period for Earth, which is, we'll measure it in years, 1 year. Okay, that's what this unit is here. That's year. Okay, and so over 1 squared is equal to 5 times 10 to the 11 cubed over t of the asteroid squared. Okay? And so here, probably cross multiply and divide and then square root your answer, and you'll get your answer. So here let's say I have 5 times 10 to the 11 raised to the power of 3 squared times 1 squared is just 1, right? So I'm going to divide it now by 1.5 10 to the 11 cubed. Okay, so that's going to apply the cube before the division. So that's 37. That's equal to the period of the asteroid squared, but I need just the basic period of the asteroid. And so I get around 6 years, or 6.1 years based on the sig figs that we have here. So T of the asteroid is 6.1A, which is the unit again for years. Okay, it comes from the French. Année is the word for year. Next question here. A satellite is placed in orbit around the Earth with an orbital radius of 2 times 10 to the 7. What is the period of revolution? Use the facts that the moon's period of revolution is this, and its orbital radius is mean orbital radius, right, is this. Okay, so now we can't use the K for the sun when we're asked about a satellite that's rotating around the Earth. We need a different K value, but we can find that K value by using another object that's rotating around the Earth, in this case the moon. So the r cubed of the moon over the period squared of the moon is equal to the K value for Earth, right, which is equal to the radius cubed of the satellite over the period squared of the satellite. All right, so since they're both equal to the K of the Earth, they're both equal to each other. I can fill this in here. The orbital radius of the moon is 3.84 times 10 to the 8 cubed. That's a 3, I promise. Let me just clean that up. There. Over the period here, they're giving us our period in seconds, which is fine. You just have to be consistent. It doesn't matter what units they give you, just have to be consistent. And so we know that we're going to get a period in seconds. And now they give us an orbital radius of the satellite at 2.0 times 10 to the 7 cubed. And that's going to be over the period of the satellite squared. Okay? Again, cross multiplying, divide, and then square root your answer. So I'm going to just be cross multiplying these two first, and then dividing by this one to get my t squared, and then I'll square root that solution. So I have 2.36 times 10 to the 6 squared times 2 times 10 to the 7 cubed divided by 3.84 times 10 to the 8 cubed. Let me make sure I've entered everything correctly. Multiply those, divide by, press enter. So this is my period right now in this is the period squared of the satellite in seconds. But of course I need to get just the period, not the period squared. And so I get a period of satellite of, let's keep 3 sig figs here. No, we're going to keep 2 sig figs here based on the question. 2.8 times 10 to the 4 seconds, okay, or 28,000 seconds. All right. So with this kind of mathematical understanding and some of the theory understanding that we looked at before, you have everything you need to answer the questions from the review 5.2. All right, we'll see you guys next time.